So I'm introducing the flat earth refraction model, and this works out for everything terrestrial and heavenly. So if we're going to have Polaris or the sun being a tangible object, then to get the trigonometry to work out, then that necessitates refraction. And just like their model, they have refraction. They have it working out to there's 0 degrees refraction if something's directly overhead. In my model, I have it to where once you get past 63 degrees, there's no refraction. Okay, so it's similar to the globe model, but what you have is from anything from the horizon to 1 degree up, you use 100% of 6 inches per mile squared. Okay, at 5 degrees above the horizon, it's 96% of 6 inches per mile squared. Okay, then it works its way down to 0 at 63 degrees. Okay, you get this a lot with when arguing with Globers about the angles to the sun, the angles to Polaris, okay, angles to the moon. So in my mind, something's got to be going on because they don't quite line up, okay, and in reality, they don't line up everywhere on the globe either. They have to use refraction, like their 7/6R for their terrestrial refraction, but this refraction model works on everything. So just to show you, based on 6,200 miles from the equator to the North Pole, so 45 degrees, we're going to go with a 45 degree latitude. So that gives us angle, or the side B, 3,100 miles. That's halfway. So triangulated, the Polaris comes out to about 3,655, and the sun and the moon are pretty close to that. But so side A is 3,655. That's the height I have to Polaris, and no matter what height you put it at, it doesn't quite work out. So just a little bit of refraction, which is what we experience in reality, is all it takes to make these right. So just to show you, if you calculate this, instead of 45 degrees, you get 49 degrees, and it gets progressively worse. So I have the model where the light's refracting about 6 inches per mile squared. Okay, and you use different percentages of that depending on the degree above the horizon. So anything from 1 degree to 0, from the horizon to 1 degree, is use 100% of 6 inches per mile squared. Okay, and anything 2 degrees above the horizon, you use 99%, and 3 degrees, 98%, 4 degrees, 97%. Then it starts progressing off till you get to about 64 degrees, when the sun or Polaris or whatever you're looking at past the horizon is 64 degrees and up, then there's 0 refraction. It's a lot like their model. They have 0 refraction with something that's straight overhead. In our model, there's really no refraction, anything that's even close to overhead. So 64 degrees to directly overhead, there's 0 refraction. So to show you how it works, okay, we'll test it. So I'll do the calculation with you. So we'll say 45 degrees. We go to my table, and that's 60% of 6 inches per mile squared. So we'll say 6,200 divided by 90, because there's 90 degrees, times 45. It's 3,100. So we go to the triangle calculator. We put in, I already have 3,100 for the angle. Okay, for side B, the distance. Okay, then we say 6 inches per mile squared. So 3,100 times 3,100 times 6. Okay, that's how many inches. So we're going to put it in feet, divided by 12. Then we'll put it in miles, divided by 5,280. Equals 910. So that's the refraction. So we're going to subtract 910 from the 3655. So we're going to say 3655 minus 910 Wait. I forgot to do, see, this is what I did live a couple times. I forgot to do the percentage of that. So one more time, 6,200 divided by 90 times 45 is 3,100. So 3,100 times 3,100 times 6 divided by 12 divided by 5,280. But then I go to my table and I see, okay, 60% at 45 degrees. So times 0.60 gives us 546. That's the refracted amount. So now we say 3655 minus 546. So 3655 minus 546 equals 3109. So now that's our new value. So now we change our value to 3109. And we calculate, and what do you get? 45.083. Okay, I'll do one more in good faith. You could check any of these. It's kind of adult. It's the same thing they have on their model there, basically. So we'll say 20 degrees is 86%. So 6,200 divided by 90 times 70, because that's what's left out of the 90 degrees at 20 degrees above the horizon. Leaves 70. So that's 4,000. That'd be the distance. 4,822. Okay. So 4822 we'll go. We'll put that in. That's the distance. 4822. Okay. Then we'll do the math. So 4822 times 4822 times 6 divided by 12. Put it in feet. Divided by 5,280 to put it in miles. That's 2201. Okay, and we said 86%, so times 0.86, that's 1893. So 3655 minus 1893. So wait, so 3655 minus 1893 gives 1762. So we go over here, we say, so the new elevated height, 1762. And what do you know, 20 degrees on the dot. So you can check all them, you know, pretty much worked it out. I just went into, rounded off every 5 degrees when I got past 10 degrees. So check it if you want, but anyway, so they can't mess with us about the angles to Polaris not lining up, because all it takes is a little bit of refraction. And you see on the graph it works out as a nice little parabola, just a steady fluent curve, which is what you would expect. Thanks.